I hope. And like it is about spherical metrics with spherical surfaces with conical singularities. And this is basically all the results which are which I will mention to you, which kind of are not by other people, is by me and Gabriele Mandela. So, and we have like two papers about this, quite long, both. 373. So the two papers, and but what I will do today, I will mainly speak about like examples and results of other people. So first, I will give you definition. So definition of what is a constant curvature surface, constant curvature surface with conical singularities. So there can be like three types of such surfaces. Curvature can be negative, positive, or zero. The most interesting case for me is like positive curvature, but still I will give a definition which holds like for everything. So definition. So a spherical Euclidean or hyperbolic surface S with conical singularities. And singularities can be just, there will be like points x1, etc., xn. So I will have something like some surface. And here I have like conical singularities, x1, xn. So what is this? This is a surface with a complete metric that has constant curvature, on the complement to these points. So if you throw away points x1, etc., xn, you get something here with constant curvature. And so points xi, they are conical points. And then, so there is a certain number associated to each conical point, is like conical angle. So how can you kind of understand what is the conical angle around this point? So you do the following. You take your conical point, and you take a circle of radius epsilon, yeah, around it. And then you just calculate the length of this circle. And then what you get. So in the spherical case, the length will be length of this thing is so spherical case, I mean something like this, yeah? So then the length is 2 pi epsilon, so 2 pi sinus of epsilon here, yeah? So this will be 2 pi sinus of epsilon and times certain number theta, yeah? So 2 pi theta sinus epsilon. And then 2 pi theta is the conical angle at the point, yeah? So in the Euclidean case, it will be, of course, the length of this circle will be 2 pi just theta times epsilon. Yeah? And in hyperbolic case, it will be something like 2 pi theta hyperbolic sinus of epsilon. Okay, so this is these are conical angles. And now, so there is a way to get such surfaces, and for me, the most natural way is basically is the following: that so it's remark, every surface, every such surface can be glued from triangles, can be glued from basically it will be like spherical, or Euclidean or hyperbolic triangles. Yeah. So basically, we take some collection of triangles, spherical triangles, for example, and we glue them by isometry. So we identify different sides of the same length, and in the end we get a surface. Okay. Yeah, I prefer compact surfaces. Yeah. I prefer compact surfaces. And now, basically, like there are two. I don't know how familiar is this object to you, but there are two kind of special cases that are super familiar. So two special cases. For example, if you have a say orbifold, say hyperbolic orbifold surface, hyperbolic orbifold surface. So namely, just take some usual like hyperbolic surface and you quotient by a finite group, which is a rotation preserving, then the resulting object will be an orbifold, and it will have conical angles. Basically, the angles will be like of the type 2 pi divided by n. Yeah. So in this case, the θ is equal to 1 over n. So this is one type of examples which is very natural. Or alternatively, you can do the following thing. You take, for example, your round sphere S2, and you consider so S2 with curvature 1, and you consider a ramified cover. Some surface just is mapped here by a ramified cover. And then there will be some points of ramification, and then you pull back the metric, and then the metric will have like angles 2 pi n, where n is like odd of ramification. Yeah. So in one case you get 2 pi divided by n. In another case you get 2 pi times n. But both are kind of nice things, and why not let this theta to be any number, any positive number. So this is, yeah? Okay. So now what I want to say is that, so why I find this kind of these things interesting is that so there is a like completely like wild difference in behaviors of these objects. So difference in behavior, like spherical versus is that just kind of is completely different from hyperbolic and Euclidean. Hyperbolic plus Euclidean. So, like in some sense, you can say that hyperbolic and Euclidean surfaces are completely understood, while spherical, they're almost not understood at all, in some sense. I will kind of speak about spherical surfaces mainly, and the title of this talk is Moduli spaces. So I will speak about moduli spaces of the spherical surfaces, and the point is that moduli spaces of hyperbolic surfaces are completely understood, and it's a very classical object which we all know, and this is maybe the main example of moduli space, because they coincide with just moduli space of marked Riemann surfaces. Okay, so first, how to distinguish spherical from hyperbolic case? So this is some useful formula, Gauss-Bonnet formula. Gauss-Bonnet. Bonnet, basically, it relates the area of the surface with the conical angles, and I will just state it. So it's like this. Let S be a surface of constant curvature, with conical singularities, with conical points. Then we have the following equality. So if we take the area of the surface, area of S, we divide by 2 pi, multiply by k, and I want, for example, k is interesting cases 1, 0, minus 1. And then here we get the following thing: the early characteristic of the surface plus sum of theta I minus 1. Yeah. So this quantity is very is an important quantity, and we see that if we just ask ourselves, we want a surface with conical singularities with given angles and constant curvature. So then how do we know what is the curvature? So we see that if this number is positive, curvature should be positive. So if this number is positive, our surface will be spherical. So it will be spherical surface with conical singularities. If this number is 0, we will get a Euclidean surface, and if this number is negative, we'll get a hyperbolic surface. And now I will finally state kind of a result which in some sense completely describes what happens in hyperbolic and Euclidean case. So this is a result, I think, of Troyanov and McCowan. Okay. So this is theorem of McCowan Troyanov. And it states the following. So basically, complete classification of hyperbolic metrics with conical singularities and Euclidean ones. So let S x1, etc., xn be a Riemannian surface with marked points, x1, etc., xn, and suppose we have numbers theta 1, etc., theta n. Suppose theta 1 and theta n are given such that this quantity is negative, yeah? That early characteristic plus sum of theta I minus 1 is less than 0. Okay? So then there exists a unique unique hyperbolic metric with conical singularities at xi, yeah, of angles 2 pi theta I, and satisfying one more property, that is scalar on the complement to these conical points, x1, etc., xn. Yeah. So Riemann surface. So so what is Riemann surface? Riemann surface is a surface with a conformal structure, basically. Yeah. Sorry.
By Keller, you mean Misha?
By Keller, I mean Keller with respect to the complex structure. Okay, maybe it's not. I see your point. So maybe it's not very kind of nice way to express it. But the point is that so we have our surface here with a complex structure, and complex structure is also the same thing as a conformal structure. Yeah. And so what I say that there will be a unique metric with conical singularities, such that basically the metric. The hyperbolic metric will be conformal with respect to in this conformal class, yeah? Okay? Thank you. By the way, it's just also, it's a very tiny remark. Whenever you have such a surface with surface with conical singularities, of course, it has a natural complex structure. Basically, this gives us a surface with marked points, because we can rotate by complex numbers at each point. So this is the statement. By the way, I don't know, Gabriel, is it correct that these are two people who proved it? Yeah. Okay, great. So. Okay. So. And then same thing holds when curvature is equal to 0. It's just that this time the metric is unique up to scale. And so now this theorem has a nice corollary, well, I mean, which is completely iobvious, immediate. So I will give you first definition. So So basically, I will say that mg n theta 1, etc., theta n, yeah, is the moduli space, of matrix, of constant curvature matrix with conical angles, angles 2 pi theta 1, etc., 2 pi theta n. Yeah. So again, the curvature will be decided by the sign of this number, and so the corollary of this result is that if this number is negative, yeah, if early characteristic plus sum of theta I minus 1 is less than 0, it follows that this space mgn of theta 1, etc. theta n is just mgn. Yeah. So this space coincides with the moduli space of marked surfaces, which is kind of, we all like this object and we know many things about it. So, and the kind of the point of this talk is kind of is to stress something, that these spaces, we know them very well, but the spaces of spherical metrics, we just don't know anything about them in some sense. Just like don't know the topology, like basically the amount of things that we don't know about them is quite bewildering, I would say. What I want to say is just to say a couple of things that we know about spherical metrics. Okay. So, questions? So now, so basically, while we were doing these things for quite a while, kind of it became, well, apparent that there are certain three questions, like school type questions, which are very important if you want to kind of to think about spherical surfaces. And so like these are like really baby questions. They're like, for me, they're like symbols of this activity. And I will now just write down these three questions. So from now on, only spherical metrics. So question number one. I mean, I will give you answers. These are questions which are kind of were all answered a long time ago, apart from the last one, which I haven't seen before. So first question. So for which theta 1, theta 2, theta 3, they're like from 0 to 1, there exists a spherical triangle with angles pi theta 1, pi theta 2, pi theta 3. This is question number one. So spherical triangle, like, I mean, in this case, you see these conditions tell me that it is convex. And what can we say about the angles? This is question number one. So question number two, slightly different. Basically, this is like this. So let L1, L2, L3, L4 be lines in CP3. Like CP3 is like a complex projective space. We have like here 4 lines. Yeah. So then, how many lines? How just let's say they are disjoint lines. Yeah. So then, how many lines? Many lines intersect these 4. These 4. Question number 2. And the last question, which the most simple one, but which I really kind of, it's a very new question. I mean, it's like, it's only 2 years old for me. So it's about like, it is the question of from topology, like topology, question 3. So like this. Which compact surfaces without boundary can be obtained from a polygon, you know, just so we take some polygon, for example, with like 8 sides. We already probably saw this, and then we start to glue the sides of the polygon. Yeah, from a polygon by identifications of edges, by identification of edges, so that all corners are glued in one point. Okay, this is a question.
What kind of matrix do you have on spherical or
Here? No. It's just a question. Sorry, it's a question of topology, like from a topological question. You take a polygon. I mean, a disk. So polygon is like you see disk with some kind of size. Topological question. Then just, you know, like in each book, like on surfaces, you have like some surfaces that you can glue from disks. Yeah? No metric. Topological question. So this question I never saw. Has anyone seen this question before? I wonder. Or maybe you know how to solve it? What's the answer?
you just put a point in a Riemann surface and you put like simple curves from this point and you cut your Riemann surface.
Very good. But what is the answer to this question? All?
Even polygonals.
Yeah. No. But no. Which surfaces? You see, the question is that which compact surfaces without boundary can be obtained this way? Sorry? Oriented. Okay. But in reality, you don't need oriented as well. Anyone want to guess?
Maybe like divide by 4 and all the genuses below that.
So first of all, from the books that we read on topology, we know that there's nothing mysterious in this question. Of course, that each surface of positive genus is obtained this way. For example, torus like this, yeah. So maybe one condition kind of is not. So you see, like when you glue torus, then all the points go to 1, yeah. So what the kind of the answer to this question is all surfaces apart from S2. So this is and this is kind of really crazy. S2 you cannot get this way. And what is interesting is that for all the story, this is like extremely important statement. So that S2 cannot be obtained from a polygon, so that all the points go to 1. For example, RP2 can, and this completely changes theory for RP2. Okay, so.
Isn't the surface uniquely determined because the Euler characteristic?
Yeah, of course, yeah. But still, yeah. So kind of, you see, the point of this thing is that whatever you do, you will never get S2, and somehow, and you prove it using an Euler characteristic, of course. But you can get RP2 like this, no, but not S2. Okay, so now I just want also to say that this question is just a historical note.
You can get S2, just reverse
Yeah, but you see the point. That's true, but there are 2 points, yeah? These are kind of different. They're not glued to 1 point, yeah? So you're right. And this is also very important, but not to 1 point. So just one historical note is kind of, for me, it's a funny thing. You see, like, so it's about Atiyah, Michael Atiyah. So he wrote like very many papers, like 300 at least, around this maybe. But his first paper, which was in 1952, was analyzing completely this question. So he kind of analyzed it completely when, for which configuration of lines, what do you get? So at the time, you could publish such a result. And it is kind of relevant to all of this. And then finally, what I want to do, because maybe in some sense the most kind of important question here is question number 1. And for this reason, I will give an answer to this question now. And for the other 2, we will just encounter them. We will encounter them later on. So this question I will delete. Okay. So it's like it's a kind of extremely important picture in this activity. So you see, we have like theta 1, theta 2, theta 3. They're from 0 to 1, and like the whole thing is a cube. Yeah. So I will draw it like this. So this is theta 1. This is theta 2. This is theta 3. And I don't know, maybe I prefer like this. It's a little bit, it's not so easy to draw the picture. Okay, so now, first I want to put here the cube, yeah? So the cube, it looks something like this, yeah? It's horrible. So in this cube, we want to find the subset, yeah? So this is 1, yeah? 1, 1, 1. We want to find here the subset of angles for which spherical triangle exists. And I will just give you the answer immediately. So what you should do, you should take certain vertices. This vertex, 1, or I will use colors. This vertex, these, and these, yeah? And now you take the convex hull of these vertices, and then basically, so what happens when you take a convex hull? Of course, you get a tetrahedron, yeah? And so the claim is the following, is that, so answer to question 1, answer to question 1, well, I mean, it is almost precise in reality, but, well, no, in reality, sorry, it's 100% precise because I asked here the angles to be between 0 and 1, so no boundary. So basically, answer is that angles A1, angles of spherical triangles, spherical triangles form the interior of the tetrahedron of the tetrahedron. And what I will do now, I will prove it. I will prove it for you because, well, I mean, I think it's kind of, maybe this is the most important kind of point of the talk, in some sense. So tetrahedron, like there are four faces. So there are 4 inequalities. Like each inequality is a face. So where from these inequalities come? One is kind of really simple. So one we say that area of delta of a triangle. There is a formula for just for the area of spherical triangle. It's like it's a cute thing. Is equal to pi theta 1 plus theta 2 plus theta 3 minus 1. Yeah. So and this should be more than 0. And this is this face. Okay. And now, what about other three faces? And I have to say, it took me, I will give you now a new proof of other results, and it took me like 10 years to kind of to come up with this proof, because before it was less convincing. So, how to prove like 1, 2, 3 other inequalities? Yeah. So suppose you have a triangle. Yeah, convex one with angles pi theta 1, pi theta 2, pi theta 3. So then what we can do, you see this triangle kind of sits in the sphere. Yeah, you can put it in the sphere and you can complete it. So it will be part of bygone. And obviously, the area of whole thing is larger than the area of the triangle. And the area of the whole thing is 2 pi theta 1. So we get that 2 pi theta 1 is greater than this. And this gives us 3 other faces. Yep. So this is the best proof, which I know. OK, great. So now I think this is a canonical kind of picture is described. And I will, from now on, I will now go to just to describe you some simple examples of spherical surfaces, which I think, again, important to understand, because well, if we can understand these simple guys, then maybe there's no chance to understand more complicated ones. Yes?
This result of spherical triangles and complex spherical triangles, there is someone to credit this. I don't know exactly how.
Hard to say. It goes definitely, probably at least to Klein, but maybe, I don't know whether maybe to Greeks, but maybe not. So I just don't know. Sorry? Maybe it could be, yeah, but no, it would be good thing to know. But definitely Klein knew about these triangles. Well, I mean, not only about this, but even about more complicated ones. But probably before. Okay, so now examples. So examples which are really important to kind of understand is namely spheres with less or equal to 3 conical points. Yeah. By the way, so here I had this notation. Yeah, I had this notation m gn of theta 1 theta n, and for spherical I will slightly change it. It will be m spherical gn of theta 1, etc. theta n. Yeah. So and our goal is kind of to understand something about this Moduli space. It's just whatever we can understand. So first, we will consider spheres with at most 3 conical points. And there are 3 possibilities here. Numbers which are less than 3, well, there is 0. Then, of course, we have a just round sphere. Then we have 1. There could be like 1 conical point. Question 2, 3. Yep. And I think this is true that these 2 cases were treated by Troyanov. And what I want to do is that I want to kind of describe to you completely what happens here, here, and here. And again, the proof is like very, very elementary. So first, let's start with one conical point. Lemma is like this. So there is no sphere with spherical metric, and one conical point, of angle 2 pi theta different from 2 pi, yeah? Okay. So I will give a proof. So it's dangerous, but because like it's kind of some statement which kind of sounds really obvious, but if you try to prove it, it is better to give a correct proof. So this is what I will try to do. Okay. So basically, so proof. So to understand this this proof, we need certain picture nearby, of a kind of standard sphere with two conical points. So like so there exist spheres with two conical points, which are like S1 invariant. So there is an isometry acting here, and this angle is certain angle 2 pi theta. So such objects exist. It's not hard to understand how to do them. For example, you just take a standard sphere, you draw here a sector, and then you glue together the shores, yeah? And then you get such a thing. This is like for angle less than 2 pi, but obviously you can do it for all angles. And in this picture, so this is kind of a canonical kind of picture, which kind of permits us to understand how a neighborhood of a conical point looks like. So for example, if we have here this sphere, like we have the neighborhood, let's say, of radius r. This is the disk of radius r, and this boundary has length, as I told you, 2 pi theta sinus r, yeah? So this is how a neighborhood of a conical point, a standard neighborhood of conical point look like. Okay, so I want to understand why there is no sphere with one conical angle. So suppose there is something like this, yeah? Like suppose we have such an object, point x1, 2 pi theta 1. So then first what I want to do is to introduce certain number. So let's find maximal R1 such that there exists an open disk, a standard open disk, open disk basically of radius R1 centered at x. Okay. So you see, of course, I mean, if I take just a little neighborhood of it, yeah, it will be just like a neighborhood on the sphere, and then this neighborhood will grow, become larger and larger. At some point, it will not be standard anymore. and the moment will kind of happen when it is not standard anymore. One important remark that R1 should be definitely less than pi. You see, this is a crucial thing. R1 is less than pi because if our standard neighborhood is very large, it just like it looks like part of the sphere, and finally everything will collapse here. So basically, there is no way to have a standard neighborhood of size more than pi. So it should be smaller than pi. Now, let us now draw this standard neighborhood. So then, what will happen is kind of easy to see. Is that what will happen is that we will have our standard neighborhood, and somehow the only way to have it is that at some point it touches itself somehow. Yeah, the neighborhood touches itself. So this is what happens. This disk touches itself. Okay. Nothing else can happen. Okay, so if the disk touches itself, so then the claim is that there is a geodesic here. There is a geodesic, yeah? There is a geodesic here of length 2 pi R1, which is less than 2 pi, yeah? We have a geodesic. So we have a geodesic. Now we cut our sphere along this geodesic. And what do we get? We get two disks, two spherical disks. So cut along gamma, cut along gamma. And then we get two polygons. So basically, one gons, okay? With spherical metric. I hope you understand this. So, like, you see, because we'll have a geodesic. Inside, we have a spherical metric, and there is just one breaking point. But now, if you think carefully, there is no one gons on a sphere apart from half sphere. Yeah. So if you just, so this one gon, we will be able to embed it inside of the sphere locally isometrically, and this geodesic, it will do something like this. And basically, it will not return back. That's it. So there is no one gons on the sphere with a side of length less than 2 pi. And the only one gon which exists is just half sphere. So contradiction. This proves to us that spherical metric with one conical singularity don't exist. Any questions?
Yeah, why don't you just consider development map? You remove your point, it's simply connected. Development map should be become more to its image, and then its image, since the diameter of the excised point is 0, it should be the host. I think it's easier.
Or
But
there's a monodromy
you're right. No, you're right. Maybe you see, maybe because this is kind of too sophisticated. But you are right. It's just that it uses some kind of technology, to which I will come, monodromy. But I think it's possible. I agree. It's possible. But for example, with monodromy, it could be trivial. For example, yeah. The angle could be divisible by 2 pi. So maybe why I'm giving this proof, because it also generalizes to two conical points. And I will not like exactly tell you how it generalizes, but I will state to you the answer. And also because it definitely, you see, it's just a complete proof. This is what I like about it. So two conical points. So two So now, what happens with two conical points? So, two conical points. Here the situation is like this. So, such spheres already exist, and here's a family, but there is a little subtlety. So there is a little subtlety. So let S be a sphere be a sphere with two conical points, and of angles 2 pi theta 1, 2 pi theta 2. Then theta 1 is equal to theta 2, and moreover, is equal to theta, and moreover, the following holds. If so, that can be two possibilities. So if theta is not integer, if theta is not integer, then the sphere is S1. There is a S1 symmetry. There is an S1 symmetry. So just like in this example which I gave you, or if theta is integer, then the sphere basically, also I mentioned this already, we have like branched covers. So the metric is obtained by a ramified cover from S2. So basically, you know, like we have one S2, and we can consider a map here which branches into points, like just, I don't know, it has like just two branching for the n here and here, and if we pull back, we get a metric, yeah? So I would say that, well, you can again prove this statement in a similar way. I would say, so here the idea would be more or less like this. I just very quickly tell you this idea. Again, you can use monodromy, that's true, but again, if you have a sphere with two conical kind of singularities, then again you can consider the smallest kind of this kind of R1. You can consider this R1 maximal size of your neighborhood. And now two things can happen. Either R1 will be again a closed loop. So either we will get a closed loop of length less than 2 pi, which is impossible, or we will get an arc of length at most 2 pi going from this point to this point. Yeah, we will get an arc. And now, if we cut along this arc, we get a bygone. And bygone, now what is funny is that bygones, they exist, yeah, but they are not all like this. So if the angle of bygone is not divisible by 2 pi, it is necessarily like this, yeah. But if the angles of bygone are divisible by 2 pi, then you can get something, for example, like this. You just take two half spheres and glue them along a segment. So there's more flexibility here. So anyway, so this kind of more or less proves proves the statement to some extent. And finally, so I think this was probably done by Troyanov. And finally, I want to say something about spheres with 3 conical points. And this is already a recent result in complete generalities, like 2004, by Yeremenko. So this is a person, Yeremenko, he classified completely spheres with 3 conical points, with spherical metric, and he kind of gave also a reference to Klein in 2000, like, 1905, something like this, who also was looking at these objects. I will not completely, I will not prove it, first of all, because it's more complicated, but I will give you the answer. So, well, how to get spheres with 3 conical points? Well, like, you can do the following. So basically, so spheres with 3 conical points. With 3 cone points. Again, you just take a triangle. Yeah, with angles 2 pi theta 1, 2 pi theta 2, sorry, pi theta 1, pi theta 2, pi theta 3, and glue it to itself, like in your talk, I think, almost, but maybe still a bit more simple, because here somehow you just glue by isometry. So because here, when we glue polygons, we don't need, like, just everything is just, because we have a metric, the gluing kind of is unique. So we just glue by isometry, and we get a sphere with 3 conical angles, yeah? And the claim is that like majority of spheres are like this. You see, majority in a sense, like up to, if you throw away dimension 1, it's just like with 2 conical points, spheres with 2 conical points, we saw that if the angle is divisible by 2 pi, then something dodgy happens. But if the angle is not divisible by 2, but if the kind of angles don't satisfy certain relation, then each sphere with 3 conical points is obtained by gluing 2 spherical triangles. And then, like, something kind of quite cute happens here, I would say. So, you see, when I kind of ask this question, when the question 1 was asked, we were asking for theta 1, theta 2, and theta 3 to be from 0 to 1. Because we kind of just, it's the beginning, and we want to understand, like, spheres with angles less than 2 pi. But what happens if angles are arbitrary? What happens to this tetrahedron? And here's kind of something nice happens. So first of all, like, let me kind of draw you a picture of some pictures of triangles inside of S2, not necessarily convex. So you see, we can have a triangle like this, yeah? Then we can have a triangle like this. Then, and somehow there is a transition this way. We can have a triangle like this. And finally, we can have a triangle, as you can imagine, like this, yeah? So complement. So these are all triangles which are embeddable into S2. And how to, what the picture that we should kind of draw here. So here, reflection group is acting. So if we are asking what are possible angles, we should do the following thing. We take our simplex and start to reflect it just with respect to the faces. So, for example, we reflect it like this here, yeah? And so on. We just go reflecting, and we'll get certain picture inside of R3. And if you are inside of one of the simplexes, there is a metric. If you're outside, there is no. So this is Trajanov's result. Sorry? things. This is Uremenko's result. Maybe, well, here maybe the one more person who did something slightly less general, because kind of the main kind of really new part of Uremenko result was to understand what happens kind of on the boundary of triangles, but because this is kind of subtle point. Anyway, so this is good. So this is about examples, and now I will go further to kind of in the direction of results. Yeah. Okay. So somehow, yeah, without drawing these pictures, I don't see how to live, like how to prove anything. Yeah. By the way, notice that what we have proven is that we understood when M spherical 0, 3 of theta 1, theta 2, theta 3, we kind of understood completely, thanks to Uremenko, we understand this object. So it's basically, if certain inequalities are satisfied, we have just a unique point in this Moduli space, just a unique metric. Okay. So now, what kind of question can we ask? So I will just kind of give again definition, the following. So definition. Just sorry for repeating, but to fix it. So fix G theta 1, etc. theta n greater than 0. So then we call M spherical Gn of theta the Moduli space of spherical matrix the Moduli space of spherical matrix with n on surfaces of genus G, on surfaces of genus G, with n conical angles, yes, sorry. 2 pi theta y. So what can we ask about these spaces? Just what is kind of the most simple question that we can ask? So questions, how to ask them? So like, I don't know, I want to share, since I have a lot of time, like some stupid joke which I heard from Arnold at some point. So basically he had like a very bad interaction, kind of, he didn't like Bourbaki, and he was making a lot of jokes about Bourbaki, and so he was claiming that there is a certain procedure. So one of these Bourbaki is supposed to be kind of thrown away from his to alt already, and he's supposed to kind of be eliminated. And so when, how to do this? So there is a Bourbaki seminar, and and there is someone giving a talk, a very complicated talk, like, and the guy is sitting in front, and then, like, it's very interesting, but in the end, what happens is that this talk is about an empty object which doesn't exist. And so if the guy in the audience doesn't understand that this object doesn't exist, he's kind of expelled from the society. I don't know whether it's true or not, but this is what I was told. So, and here, so first question, which is kind of similar in nature, is that when the space is non-empty. So, question, when is M spherical of Gn theta is non-empty. And well, so there is one kind of one obvious constraint is the following, is that we saw that, so one constraint, Gauss-Bonnet. And this tells us again that, area of S is equal to 2 pi times this, theta I minus 1. So this should be greater than 0 for sure. So if we want the space to be non-empty, but now, so basically the theorem which I will speak later on is kind of this can be so kind of theorem like which I obtained with Gabriele. So a more recent one is if G is greater than 0, this is the only constraint. This is the only constraint. And if G is equal to 0, the answer is really more complicated, but it's kind of pretty. And as you can see, like the answer should generalize this kind of collection of simplices somehow. It will be like certain, there will be certain inequalities, periodic system of inequalities. And if G, I will probably already speak about this on next time. If G is equal to 0, the answer is more complicated. The answer is more complicated. But somehow also can be given by one inequality in some sense. As this picture of simplices can be obtained by one inequality. So, and what I want to explain now is just very quickly why G greater than 0, we have only one constraint. So why is it so? It's kind of, again, the main, so when you kind of prove it, there is a kind of a lot of technology, like some amount of technology going inside. But the main idea is question number 3. You remember, question number 3 was what? Which surfaces can you get from polygons? Yeah. So use maybe so G greater equal to 0. Use question number 3. Use question number 3. So what question number 3 was telling us? It was telling us that whenever we have a surface which is different from sphere, we can glue it from a polygon. Yeah, from a polygon by identifying its sides, so that everything is glued to one point. Now what we do, basically, it's enough to prove this kind of, to give this answer. In some sense, it's not quite true, but in some sense, it's enough to construct a surface with one conical singularity. So how do we do it? We just take of any given area. Yeah. So we take a bigone, and now we cut it into, for example, in like 2n equal sides, and then we just do this standard procedure. Yeah. And when we do such a thing, we get a sphere, we get a surface. In this particular case, it will be surface of genus 2 with one conical singularity. And what is important is that in this construction, which is kind of very simple, this angle can be arbitrary. So you can get a sphere, surface with any area this way, because bigones kind of they can have arbitrary area. So now we get a surface with one conical singularity. And once you have a surface with one conical singularity, what kind of you do? There is a kind of technology of splitting such a conical singularity nearby, like in in many others. So you do this and everything works. So this is how basically moral of the proof. It fails completely if you are dealing with a sphere, because for a sphere you cannot get a surface with one conical singularity, and you get this kind of pretty picture, which is described here. Okay, so now, basically what I will do is that I will list. So suppose we know that spherical. So this moduli space is non-empty. Suppose we know that it is non-empty. So then, again, for hyperbolic manifold, for hyperbolic case, we knew everything about this moduli space. We knew that it is just isomorphic to the moduli space of curves with marked points. So what can we say about spherical guys? So here's the list of questions which I want to address. Soon. Okay, so this is like kind of we're coming to basically more like following slightly more refined questions. So suppose that that M spherical G n theta is non-empty, empty. And then, well, I mean, there's so many questions you can ask because we don't know anything about them. For example, is it connected? Is it connected? Well, of course, moduli space of pointed curves of genus G is connected. So, is it connected or not? Second, now we have a forgetful map. Yeah, so we have a forgetful map from a. So we can start with a surface with a spherical metric, and forget the metric and just get a complex structure. So, is the forgetful map? Is there forgetful map? Forgetful map M spherical Gn theta to mgn surjective. Sorry? Look, what is diffeomorphism? No. But it's kind of, it's, no, I mean, there is no way. I mean, and this is why it's interesting, I would say. Yep. But I mean, this is already a kind of follows from, well, this is kind of not a news, which is, but okay, anyway. Well, next, well, I mean, this is question is like, does, I mean, all these questions are very kind of, first come to mind, does this map has finite fibers, and finally, what is its degree? What is its degree? So this is a kind of definitely not. But I mean, it's not open. But you can also ask. I agree. But this maybe I don't want to ask it because. Okay. So. Yeah, it's a good question as well. It's a good question. In reality, answer is completely unclear. So it has a symplectic structure, but the complex structure somehow, well, as far as I understand, so I kind of, for me, yeah, why should we have complex structure? So I will give you some examples when it has a complex structure, and this map is holomorphic. So it kind of, when you first look at this, you would say, oh, maybe yes, but in reality, no. So it is not. So, and okay, so now answers. So, which I will speak to you about. So first theorem. So first theorem is like with Gabriele. Is that it's just one kind of example. The space. I think it's interesting to have such a statement because nothing kind of very little is known, and this is why this is kind of not bad. So such a space, spherical surfaces on with conical singularities with certain angles can have great or equal to 3 power n connected components. So this is basically, it could be that the examples which we can handle, there is an inequality, but still, the number of components can be big. So this is first. Second, so here I will leave just a little bit of suspense for the next time to kind of reflect the drama which I had myself because kind of anyway. So 3. So here is interesting. So there is a paper of very recent paper of Yeremenko. It's May 2019, and it is very really I would say for me this paper looks quite kind of subtle. So he proves that in case of M spherical 0, 4 theta such that this number theta 1 plus minus theta 2 plus minus theta 3 plus minus theta 4 is not an even integer, yeah, then indeed in this case the number is finite, but no clue what is the number. And finally 4. So this is it's an older result. I mean, just again, it's quite recent still. Is Chen Lin. They can calculate the degree. Calculate the degree of the map. Calculated the degree. In case if chi of this thing plus I plus minus theta I is not into Z plus, yeah? So the calculated degree is a very kind of interesting formula, which I don't understand. And in some sense, this 4 lines is one of the cases. So they calculate this degree, and this is using analysis somehow, which I don't know. So I think I should stop here. So basically, I will speak about, first of all, I will just go on telling you about when is this kind of space non-empty. So there is a kind of pretty picture which generalizes collection of simplices, and then why that this space is it surjective, and then why there are so many components. So that's it. Thank you.
Questions, comments?